we now learned entity relational model, and now you can map a real-world question into a logical model, conceptual model and logical model. However, there is still an issue. The issue is that there are multiple ways of mapping. For the same real-world question, you can map into different entity relational models. So not all models are created equal. We always say it's like the movie name, the good, the bad, and the ugly. And same thing applies to relational data modeling. Bad models, bad designs can happen, do happen, and will always happen a lot, right? If you go out, once you finish your work and go out and taking projects, you will see bad designs every week, every month. So when we say bad design, that doesn't mean they don't work. Bad designs usually function in a limited way. However, because the way they design is not optimal, it's difficult for people to use the database, to flexibly use database. Usually, bad designs only allow you to use database in one or two very specific way. It's not extendable. And it increases the cost of usage. It make it very hard to maintain, very hard to upgrade. So this is the issue with the bad design. Improving bad design is a highly skilled and well-paid job. It's called a data architect. As a data science student, you guys are still a little bit further away from this data architect job, but it's always good to keep design principles in mind for even starting from your local design. It will help you with a local design with your own work. So let's take a look at the example of bad modeling. I believe all of you have seen some registration forms like this one before, either in the doctor's office or in some school office or in any like job application form, something like that. So we have the registration form of a company called Data Force Academy. You have a student called Luke Skywalker living somewhere in Tatooine. And you have an invoice number and the date, registration number and date. And within this registration, you have multiple courses that Luke Skywalker registered. There's 3 courses here. Now, the easiest way or the worst way of designing, of course, is to consider this original registration form as if it's a one entity. So every field on the form becomes an attribute of the form, of the relation. Because we don't have enough space to display, so I just remove some of the field, but I think you like student ID, but I think you can get the point. We have a student name, address, zip code, all this student information with registration information, ID and date, and with course, all the course take. And because each registration can have multiple courses, so we are repeating here for this Skywalker, we have 2 or 3 courses listed in the same registration for registration inside the same registration. So when you put the shorthand representation of this relation, it's a relation called registration, and you have a parenthesis with the attributes. The only thing we didn't see before is because course itself is repeating. So I need to put a parenthesis here to tell the reader, to tell whoever read this representation that this is a repeating one. This is some sub-entity inside the entity, sub-relation inside the relation, right? So there are multiple issues with this design, but basically if we categorize this design, there are 2 key issues. One is called non-atomic value, and one is called duplication of information. Both are functional dependency issues. So let's take a look at the first issue, which is non-atomic value. What does non-atomic value means? Basically, when you look at the relational model, we stated clearly that in a relational model, you have a set of tuples, and tuples have elements. And when we design this, when we create this model, this is a 3-level hierarchy relation, tuple, element. Each element, we expect it to be atomic, that you can get a final number, final value from this element. If, however, this element is a repeating group or is a nested value, then it's no longer atomic. For example, in our example, right, this course is actually an element inside this relation. You have one element here, and you have another element here. So there are actually two elements. This is no longer one single element. It's a set of repeating group or repeating groups for an entity. That's what we signify here. Registration have student ID, etc. And we are repeating a course data set. So we have, this is what we call repeating group. You have multiple elements inside in the position of what should have be one simple element. The second issue is nested group, the nested value. Nested value is when you combine multiple values into one element, right? They're supposed to be multiple elements, but you will combine them together. For example, how many times did you see someone doing this? You put a course ID instead of a course code or course ID and the course name, two different values. You are concatenating them into one. And it says this is DS530 big data. Or sometimes may not be someone combine them, but the data comes from a source that combines them. And you just inherited that. You are inheriting an element that is supposed to be multiple elements. So this is called a nested value. What's the issue with this non-atomic value? Either way, in both cases, the problem is when you try to access a certain value, you cannot do that in one step. You have to do two steps. You have to get the tuple in the original relation. Inside this tuple, you get the element. Then you have to break this element down, either by breaking that set repeating group into different small element, or by breaking up the element into smaller pieces. And sometimes you may even need to combine them to combine these two steps. So the problem is, we mentioned that it comes to functional dependency. The issue is some values like this course name or instructor, they have to be determined by the combination of keys, not only the registration key, right? Because inside registration, there are multiple courses. Then in order to get this course name or course or instructor, you have to go to the relation first and get into the course. And eventually you are determining this value by getting the registration ID, registration primary key, and the course primary key. You have to go inside the subrelation in the relation. Once you have this subrelation inside the relation, the ultimate concern is this will start a recursive pattern of design. What makes, because once you have a subrelation inside the relation, you may have sub-relation inside this subrelation, right? Then we have a three sub relation inside the two sub relation. Then this will become recursive, and this is breaking the whole ground of a relational model. Relational model is supposed to be a three-layer model. Simply, you go to the third level, you should get that value. This is how it makes the whole modeling simple. But non-atomic value break this rule and make the whole relational model not workable. And data created like this, model created like this, are not manageable by relational model and not manageable by SQL. You cannot use SQL to run against something like this, to some model like this. Now, I'm not saying this is completely wrong. There are models created like this nested model, document model. These are okay on their own domain. I'm just saying that if you want to design using relational model, you cannot have non-atomic value. Now, the other issue with our current model is it have duplicated data. it have not unnecessary dependency on non-key columns. There are values that are not necessarily needed. Let's say we already see, if you still remember the model, we have Luke Skywalker and all its address. If Luke Skywalker have multiple registrations, right? If he take one registration today and decide to have another registration for another 2 courses tomorrow, he can have 2 registration tuples. In both tuples, you have his address, a long name, the long address, and the city and the state and the zip code. Now, the problem with this is the address is actually depending on Luke Skywalker itself, not on the registration. Just because you take a new registration does not mean that you will change your address. The address will stay the same, right? But when Luke decide to move from Tatooine for somewhere else, then you have to update each and every occurrence of this address, of his record, right? The same operation must be performed in multiple locations. This is some performance hit because basically we already see how relational database management system handles SQL processing. When you try to update this form, you need to go through row by row. And it can be a huge performance hit if you need to perform this in multiple places. And also, if you accidentally missed some update, there might be inconsistencies. So in this case, you will see 2 records. If you miss updating one, you will see 2 records of Luke Skywalker. One lives in Tatooine, one lives somewhere else. How do you consider this inconsistency? Is that because he actually have 2 addresses, or is that because there's a missing update? So this will cause confusion and will lower the efficiency of your database processing. That brings us to the concept of normalization. Normalization is the process of structuring a relational database in accordance with a series of so-called normal forms in order to reduce data redundancy and improve data integrity, which means normalization is a process that we remove non-atomic value and remove redundant data. Normalization is defined with normal form. It's a formal set of rules to check against the table. Now, if you look at the table, you use this normal form to evaluate, to serve 2 purposes. One, you use this normal form to evaluate a relation. Does it meet certain quantity? If it does not meet the quantity, then normal form, together with normal form, you also have a set of rules helping you to improve your relation to achieve a certain normal form. So we say a table is in certain normal form compliant if it meets certain criteria and achieves certain level of dependency properties. If it's not in certain normal form, then there's a series of ways to improve the table quality so that it becomes certain normal form compliant. Multiple levels of normal forms exist from the first normal form to 6 normal form with 2 more derived forms. Now, the higher level of normal form, the higher level of data consistency you will have. So first normal form is the lowest level. It's easiest to achieve, but it still has some issues. So it still have some issues in like duplicated data, etc. Then you will move from first normal form to second normal form, resolving some of the data duplication issue. Then you can move from second normal form to third normal form, resolving yet more data consistency issue. As you move along the way, you are achieving better and better data. You are removing more and more data redundancy. And you have to achieve the lower normal form first in order to achieve the higher normal form. So you have to be in first normal form first, then you can move into second normal form. Then once you achieve second normal form, you will do something to achieve third normal form. If you are in third normal form, that guarantees that you are already first normal form compliant and the second normal form compliant, and all the way, and so on and so forth. Now, usually, third normal form is good enough for real-world applications. That's what we are going to teach in this class. You don't need to worry about fourth, fifth, sixth normal form and the derived forms, because those are like only dealing with very specific scenarios. And even if you run into these issues, usually it's okay to keep them as is. A little bit of redundancy does not hurt the database. But the effort to make things 6 normal form compliant can be painful. So how do you move from one normal form to a higher one, or from no normal form to first normal form? Normalization is generally achieved by decomposition. It's a process of breaking up or dividing a single relation into 2 or more relations. The idea is, as the relation has fewer columns, as you break up a larger relation into 2 or more smaller ones, the relation has fewer columns. Its functionality, its functional dependency becomes simpler to handle, right? When you have 100 columns, of course, the functional dependency is much more complex than a relation have 20 or 50 columns. And then 20 or 50 columns is more complex than the relation with 10 columns. So that's certainly understandable. And we will always start from first normal form. We will check if a table is first normal form compliant. If not, then we will decompose it to first normal form. And there are also like a standard approach to achieve first normal form. Then once it achieves first normal form, we will check whether it's a second normal form compliant. If not, then there are also ways to move from first normal form to second normal form, and so on and so forth until we achieve third normal form.